You hear all these terms, right? Deep learning, neural networks, backpropagation. It sounds super complicated, maybe even a little intimidating. But honestly, it doesn't have to be. What if we could just build a learning machine together from the ground up, right here? Okay, let's do it. This entire world-changing field of AI all started with a surprisingly simple idea. What if we just copied the human brain? On the left, that's a biological neuron, the basic building block of you and me. And on the right, that's our artificial version. And that resemblance is totally on purpose. We are literally trying to reverse engineer the most powerful computer on the planet. So here's our game plan. First, we'll look at that single artificial brain cell. Then, we'll see why one isn't enough and why we need a whole crowd of them. After that, we'll figure out how the machine gets its grades, how it actually studies to get better, and finally, we'll cover some pro-level tips for making the training process way smarter. All right, first things first, we have to start with the absolute core of it all. We need to translate that squishy biological neuron into something that works with math. This is the atom of every neural network in existence. And this is it. It's called a perceptron, and it works kind of like you'd expect. It takes in a bunch of signals, those are the inputs, it gathers them all up in the middle, and if the total signal is strong enough to pass a certain threshold, it fires. It sends out its own signal. Simple, right? But this is the key to everything that follows. So, how does a machine actually learn? It all comes down to tuning two little things: weights and biases. Think of the weights as volume knobs for each input. If a weight is high, that input is shouting and really important. If it's low, it's just whispering. And the bias? That's kind of like the neuron's default mood. Is it eager to fire or does it need a lot of convincing? These are the knobs that the network is going to tweak over and over again until it gets the right answers. But here's the catch. A single neuron all by itself is, well, it's not that smart. It can learn to draw one straight line to separate two groups of things, and that's about it. The problem is, the real world is almost never that simple. It's messy. So if one neuron just isn't going to cut it, what do we do? Well, we do the same thing our brains do. We build a network. We connect a whole bunch of them together, and this is where the magic really starts to happen. Just look at this. This is what we're actually up against. The real world is messy. The data is all intertwined. You can see the pink and cyan dots are all mixed up. A single straight line has absolutely no chance here. This is the exact kind of problem that had early AI researchers totally stumped. I mean, just think about it for a second. How would you do it with just one line? There's no way, right? A simple model is completely powerless against this kind of complexity. And this is the solution. It's beautiful. We don't use one neuron. We use a whole bunch of them, stacked in layers. Watch what happens. With just 3 neurons, the line starts to bend a little. With 6, it gets way more flexible. And with 20, the network can learn to draw this incredibly complex, squiggly boundary that perfectly separates the two groups. That's the power of the crowd. Okay, so what's the secret sauce? What's the mathematical trick that lets the network bend and twist its thinking like this? It's something called an activation function. Basically, it upgrades each neuron from a simple on-off switch to a much more sophisticated dimmer switch. And this one little change, this injection of what we call nonlinearity, is what unlocks the network's power to learn these incredibly complex patterns. Okay, so we've built our network. It's got all these neurons ready to go. But how does it know if its answers are any good? How does it know if it's right or completely wrong? Well, it needs a teacher. It needs a report card. And this is it. It's called the cost function, and you can think of it as the network's personal tutor. It's a really simple idea. Every single time the network makes a guess, the cost function compares that guess to the actual right answer, and it spits out a single number, an error score. The bigger the number, the more wrong it was. The entire goal of training is to get this number as close to 0 as humanly possible. So, knowing you got a bad grade is one thing, but knowing how to study to get a better grade next time, that's the real trick. Our network needs a system, a method for improving its score. And that method is an amazing algorithm called gradient descent. I want you to picture this blue curve as a giant valley of all the possible wrong answers. The ball is our network's current error score, sitting somewhere on the side of that valley. The algorithm calculates the slope right where the ball is, and it takes a small step in the steepest downhill direction. Over and over and over, it takes another step downhill until it finally settles at the very bottom, the point of the lowest possible error. But hold on. In a network with maybe millions of those little weight and bias knobs to tune, how does each individual one know which way to turn? That, my friends, is the absolute magic of backpropagation. This is the engine that drives gradient descent, and honestly, it's the breakthrough that made all of modern deep learning possible. Let me show you how it works. After the network makes a guess and gets its error score, that score is sent backwards through the network. It flows from the output layer on the right all the way back. And as it travels, it uses a bit of calculus to leave a little note for every single connection it passes, basically saying, hey, you contributed to the final error by this much, so next time adjust yourself just a little bit in this direction. It's this incredible feedback loop for assigning blame and credit across the entire system. All right, we have all the core pieces of the puzzle now. We get it. But in the real world, when you're dealing with truly massive amounts of data, you need a few more tricks up your sleeve to make the training process actually work without taking a million years. I mean, you can't feed the entire internet to a network all at once, right? It's just too big. So you chop it up into small, manageable chunks called mini-batches. The network studies one batch, adjusts its weights a little bit based on what it learned, and then moves on to the next batch. Once it's seen every single batch one time, we call that a single epoch of training. Now, we have to talk about one of the biggest traps in all of machine learning. It's a problem called overfitting. This is what happens when a network gets a little too good at its job. It doesn't just learn the important patterns in the data, it starts memorizing every single tiny detail, including all the random, useless noise. This is the perfect way to think about it. It's like that student who just memorizes every single page of the textbook, word for word. They'll ace all the practice questions, no problem. But then you hit them with a question on the final exam they've never seen before, one that requires real understanding, and they completely blank. The network has to learn to generalize, not just memorize. So how do you stop a network from just memorizing everything? Well, one of the clever solutions is a technique called dropout. And get this, all it does is randomly tell a certain percentage of the neurons to just take a break during each training step. They're just turned off. This forces the other neurons to step up and actually learn the material, so the network can't rely on any single neuron to know everything. It's basically forced teamwork for your AI. So let's put it all together. You start with a neuron, the basic block. You connect them into a network to handle complexity. The network makes a guess. The cost function gives it a grade. Gradient descent and backpropagation tell every single weight how to study better. And you just repeat that loop over and over, sometimes for thousands of epochs. That, right there, is how a machine learns. From spotting diseases in medical scans way earlier than a human can, to creating unbelievable art and music, these networks are already fundamentally changing our world. So now that you've seen what's under the hood, the real question is what's next? What seemingly impossible problem do you think is going to be solved by a machine that learned, step by step, just like we saw here?